Today's video is a discussion on time domain representation of linear time invariant systems, popularly called as LTI systems. We have already seen that the LTI systems could be represented in time domain as either a convolution integral as in the continuous time case, or as a convolution sum as in the discrete time case, or as a linear constant coefficient differential equation or difference equation as in the continuous or discrete case, block diagram representation, and state variable description. This video is going to be a discussion on linear constant coefficient differential equation or the difference equation. Let us go on to see what is the linear constant coefficient differential equation in the continuous time domain. The general form of the linear constant differential equation is summation k is equal to 0 to n ak d power k dt power k yt, that will be equal to summation k equal to 0 to m bk d power k dt power k xt, where ak and bk are constant coefficients of the system and xt as usual is the input applied to the system. Y of t is going to be the resulting output. Let us consider the difference equation. The general form of a linear constant difference equation is sigma k equal to 0 to n ak y of n minus k is going to be equal to summation k equal to 0 to m bk x of n minus k, where as in the previous case we are quite familiar now that ak and bk represents the constant coefficients of the system, and as usual x of n is going to be the input applied to the system and y of n is going to be the resulting output. The order of the difference equation or the differential equation generally represents the number of storage devices in the system, and usually the value of n is greater than m, thereby resulting in an order which is going to be defined only by n. This is so because, as is in the usual case, the number of components representing the input will generally be less than the number of components representing the output. Thus, the order is usually defined by the output terms. In other words, it is similar to the numerator by denominator in control systems, where the denominator generally controls the order of the system. Next, let us go on for the differential equation example. A RLC circuit is given for consideration to obtain a differential equation. In this particular RLC circuit, we can see that x of t is a voltage which is going to be the input, R, L and C are the resistance, inductance and capacitance, and y of t is the current which represents the output. So, the expression for a differential equation of a RLC circuit as is seen could be written as R into y of t plus L into d by dt of y of t plus 1 by c integral minus infinity to t y of t d tau is going to be equal to x of t. However, we would like to convert it into a complete differential case. Hence, differentiating both sides with respect to t, it would be obtained as 1 by c into y of t plus r into d by dt of y of t plus L into d squared by dt squared y of t is going to be equal to d by dt of x of t. The differential equation thus describes the relation between the current y of t and the voltage x of t in the circuit. The order of the equation is, as can be seen, equal to 2, which represents two energy elements present in the circuit. Thus, the order of the system is going to be 2. Next, let us go on for the difference equation. The example of a difference equation is y of n plus y of n minus 1 plus 1 by 4 y of n minus 2 is going to be equal to x of n plus 2 into x of n minus 1. This particular difference equation represents a relation between x of n and y of n and is helpful for processing data in a computer. Again, if we observe, we would see that the order is going to be equal to 2 and it has a value of y of n minus 2 as the maximum case, which represents the number of memory elements, which is 2 in the system output. Each of these tells us that this requires one memory element and this requires next memory element, thus giving us that similar to the energy elements in the differential case, the memory elements rule the order in a difference equation. As is given, memory in a discrete system is equivalent to energy storage elements in a continuous time system case. Let us go on to a simple problem to calculate y of n at various points n is equal to 0, 1, 2 and 3 for a first order recursive system defined by x of n is going to be equal to u of n and y of minus n is given as minus 2. Thus, we get the expression as y of n is going to be equal to x of n plus 0.5 y of n minus 1. On substitution of the given expression for calculating the value of y of n with 0, the expression becomes y of 0 is equal to x of 0 plus 0.5 into y of 0 minus 1, which is y of minus 1, and this becomes equal to 1 plus y of minus 1 as is given here is minus 2. So substituting this 0.5 into minus 2, hence this is going to be equal to 0. Similarly, we can calculate y of 1, y of 2 and y of 3. Let us go on to the calculations in each case. Y of n is going to be equal to x of 1 plus 0.5 into y of 0. Y of 0 is 0, hence this is going to be dependent only on x of 1, which is going to be u of 1, which is going to be equal to 1. Since x of n is dependent on the step input, it is clear that at all instants of time, the value of x at x of 1, x of 2, etc. will be 1. Next, let us try to evaluate y of 2 is equal to x of 2 plus 0.5 into y of 1. The solution is going to be equal to 1.5. What about y of 3? In a similar way, y of 3 is going to be equal to x of 3 plus 0.5 into y of 2, which is going to be equal to 1.75. Hence, generally the complete solution of a system is represented in two terms. The complete solution y is given by y of h plus y of p, where h represents the homogeneous solution and p represents the particular solution. Let us go on to see how a homogeneous solution could be got while solving differential equation and difference equation. Homogeneous solution could be got by setting all the terms including the input to 0. Thus, applying it for a differential equation, let us go back and consider the expression of the differential equation. It is got by setting the expression of the homogeneous differential equation would be equate this particular term to 0. So, this becomes summation k equal to 0 to n ak d power k dt power k y of h t is going to be equal to 0. And the homogeneous solution for a continuous time case is of the form y h of t is going to be equal to I equal to 1 to n ci e power Rit, where Ri are the end roots of the characteristic system. In order to get the homogeneous solution for a discrete time system, we need to equate sigma k equal to 0 to n ak yh of n minus k to 0. So what would be the solution? The solution would be represented as yh of t is going to be equal to summation I equal to 1 to n ci ri power n, where ri are the end roots of the characteristic system. Let us go on to see the homogeneous solution for a continuous time systems. If there are distinct roots, the solution is generally given by Ci e power rit plus C2 e power r2t when n equal to 2, which means when the order of the system is 2, the expression is going to be C1 e power r1t plus C2 e power r2t. For repeated roots with n equal to 3, the solution becomes Ci e power rit plus C2t e power r2t plus C3 t squared e power r3t, which means the three roots are getting repeated. If there are only two roots, the expression would have only these two terms. Next, let us go on for considering the homogeneous solution for a discrete time system. For distinct roots n equal to 2, the solution is going to be C1 r1 power n plus C2 r2 power n, where r1 and r2 are the roots of the equation. Repeated roots with n equal to 3, in the case of a discrete time system, the homogeneous solution is going to be of the form C1 r1 power n plus C2 n into r2 power n plus C3 n squared into r3 power n. Now let us go on to some simple problems on the homogeneous solution for a continuous time system. Let us consider the problem given here in the first case as d squared by dt squared y of t plus 5 into d by dt of y of t plus 6 into y of t is going to be equal to 2 into x of t plus d by dt of x of t. This could be represented in simple terms as y double dot of t plus 5 into y dot of t plus 6 into y of t is going to be equal to 0, where double dot represents the second order differentiation and single dot represents the first order differentiation as is considered in the general representation for mathematics. So the solution of this is got as y of 3 plus y of 2 is going to be equal to 0. So the repeated roots would be equating these two to 0. R1 is going to be equal to minus 3 and R2 is going to be equal to minus 2. The homogeneous solution is going to be represented as yh of t is going to be equal to C1 e power r1t plus C2 e power r2t. Let us try to find out what is r1 and r2. When we have r1 and r2, this is going to be r1 plus 3 is going to be equal to 0, which means r1 is going to be equal to minus 3, and in the second case we would have r2 plus 2 is going to be equal to 0, which means r2 is going to be equal to minus 2. Thus, the solution for this particular problem is yh of t is going to be equal to C1 into e power minus 3t plus C2 into e power minus 2t. Let us go on for one more problem on finding out a homogeneous solution for a continuous time system. Let us consider the problem as d squared by dt squared y of t plus 6 into d by dt of y of t plus 8 into y of t will be equal to d by dt of x of t. This could be represented as y double dot of t plus 6 into y dot of t plus 8 into y of t is going to be equal to 0. And the solution for this is going to be y plus 4 into y plus 2 is going to be equal to 0, which means we would be getting the roots as r1 is going to be equal to minus 4 and r2 is going to be equal to minus 2. Hence, considering the solution of the homogeneous case in the continuous time, yh of t is given by c1 e power r1t plus c2 e power r2t, and getting this in this form, r1 plus 4 is going to be equal to 0. Thus, as mentioned before, r1 is going to be equal to minus 4 and r2 is going to be equal to minus 2, as we are equating r2 plus 2 is going to be equal to 0. Thus, the homogeneous solution for this particular problem is going to be equal to yh of t is going to be equal to c1 into e power minus 4t plus c2 into e power minus 2t. Let us go on to the next discussion on homogeneous solution for discrete time systems. The expression given here is y of n minus 9 by 16 y of n minus 2 is going to be equal to x of n minus 1. Equate this term to be equal to 0, which means y of n minus 9 by 16 y of n minus 2 is going to be equal to 0. This could be represented as r squared minus 9 by 16 is going to be equal to 0, and hence r1 and r2 could be obtained as 3 by 4 and minus 3 by 4 respectively. And the solution of the homogeneous case for a discrete time is considered as yh of n is going to be equal to c1 r1 power n plus c2 r2 power n. As was mentioned before, the roots are 3 by 4, minus 3 by 4 and plus 3 by 4. Hence, this is what is obtained on simplifying this. r1 minus 3 by 4 power n into r2 plus 3 by 4 power n is going to be equal to 0. That is the solution of r squared minus 9 by 16 equal to 0. Thus, the solution of the homogeneous case for a discrete time system is going to be represented as yh of n is going to be equal to c1 3 by 4 power n plus c2 minus 3 by 4 power n. Let us go on to one more problem on the homogeneous solution for a discrete time case. This is obtained as y of n minus 1 by 4 y of n minus 2 minus 1 by 8 y of n minus 2 is going to be equal to x of n plus x of n minus 2, as can be x of n minus 1. As can be seen in the previous case, for the homogeneous solution, let us equate the output to be equal to 0. So, we would be getting it as r squared minus 1 by 4r minus 1 by 8 is going to be equal to 0. The solution of this would be r1 minus 1 by 2 power n into r2 plus 1 by 4 power n is going to be equal to 0. And the general homogeneous solution is represented in discrete domain as yh of n is going to be equal to c1 r1 power n plus c2 r2 power n. Thus, the solution of the discrete time domain problem is going to result in yh of n is going to be equal to c1 into 1 by 4 power n plus c2 into minus half power n. Next, let us go on to see how we can obtain the particular solution, as we have discussed that the complete solution is a combination of homogeneous solution and the particular solution. The particular solution for a continuous time case is given as for a particular input, particular solution is obtained, hence the name particular solution. Let us consider the various possibilities that exist for input and their respective solutions. Let us go on to the first case. When the input is 1, the particular solution is C. When the input is T, the output is going to be, that is the particular solution is going to be C1t plus C2. When the input is e power minus at, the solution is going to be C into e power minus at. And finally, when the input is cos of omega t plus phi, the solution is going to be C1 cos omega t plus C2 sin omega t. The particular solution for a discrete time case is also defined in a similar manner. The table is given here for future references. It is given as for an input of 1, the particular solution is C. For an input of n, it is C1n plus C2. For alpha power n, it is C into alpha power n. And for a cos input, that means cos of omega n plus phi, it is C1 cos omega n plus C2 sin omega n. With this understanding on the particular solution for continuous time case and a discrete time case, let us now try to analyze some simple problems for continuous and discrete time cases. Let us go on to problem solving for particular solution of continuous time systems. The problem given here for consideration is phi into d by dt of y of t plus 10 into y of t is going to be equal to 2 into x of t. And it is given that x of t is going to be equal to 2, which means it's a constant. Hence, the solution is going to be equal to yp of t is going to be equal to c. And on substituting this here, since it's a constant, this term is going to be equal to 0 plus 10 into c would be equal to 2 into x of t, which is again going to be equal to 2. This means 10c is going to be equal to 4, or c is equal to 2 by 5. Any guesses what would be the solution of yp of t? Yp of t is going to be equal to 2 by 5. Let us go on to consider the next problem for particular solution on continuous time systems. The problem given here is phi into d by dt of y of t plus 10 into y of t is going to be equal to 2 into x of t, where x of t is going to be equal to e power minus t. The particular solution for a input whose form is e power minus t is given by yp of t is going to be equal to c into e power minus t. Substituting this in the above equation, we will be getting it as phi into d by dt of c into e power minus t, which means minus of c into e power minus t, resulting in minus phi c into e power minus t, plus 10 into yp of t, which is c into e power minus t, is equal to 2 into x of t, which is e power minus t, and hence the expression that we get on substituting yp of t in the differential equation given above with the respective input is minus 5 c into e power minus t plus 10c into e power minus t will be equal to 2 into e power minus t. Let us equate the powers of e power minus t. So we get the expression as minus 5c plus 10c will be equal to 2, or c will be equal to 2 by 5. Hence, what would be the solution of the particular solution for the continuous case? It is going to be given by substituting yp of t is going to be equal to 2 by 5. We get it as yp of t is going to be equal to 2 by 5 into e power minus t. Let us go on to one more problem in the continuous time case involving a cosine term as the input. For the same differential equation, we are going to consider the input as cos 3 of t. So, the expression for the particular solution is yp of t is going to be equal to c1 cos 3t plus C2 sin 3t, considering that the input is x of t is going to be equal to cos 3 of t. From the table we know that the particular solution is going to be of the form of cos and sin with the specific constants. And now let us try to obtain what would be dy t of dt. It would be obtained as minus 3c1 sin 3t plus 3c2 cos 3t. Substituting this in this particular equation, we would be getting it as 5 into dy dt by dt is going to be equal to 5 into minus 3c1 sin 3t plus 3c2 into cos 3t plus 10 into yp of t, which is given by this. So c1 cos 3t plus c2 sin 3t, and that will be equal to 2 into the input, which is cos 3t. How can we find the constants c1 and c2? The best way is to equate the coefficients of sine and cos. So we will be getting it as equating the coefficients of sine, minus 15c1 plus 10c2 is going to be equal to 0, and similarly 10c1 minus 15c2 will be equal to 2. Thus we get that c1 is equal to 4 by 65 and c2 is equal to 6 by 65. So the solution of yp of t is going to be equal to yp of t is going to be equal to c1 cos 3t plus c2 sin 3t, which is going to be equal to 4 by 65 cos 3t plus 6 by 65 into sin 3t. Let us go on for one more problem on particular solution. The problem given here is y of n minus 2 by 5 y of n minus 1 is going to be equal to 2 into x of n. X of n is defined as 2 into u of n. Hence, the solution for yp of n is k into u of n. So, substituting this, we get it as k minus 2 by 5k will be equal to 2 into x of n, which is going to be u of n. So, it is going to be 4. Thus, k is equal to 20 by 3 and yp of n is 20 by 3 into u of n. As yp of n is k into u of n, it will be equal to 20 by 3 into u of n. Let us go on for a problem on particular solution for discrete time systems given by the equation y of n minus 1 by 4 y of n minus 1 minus 1 by 8 y of n minus 2 is going to be equal to x of n plus x of n minus 1, where x of n is given by n into u of n. The solution for the particular solution case is given by yp of n, as from the table, is n into k1 u of n plus k2 u of n when the input is n into u of n. This is the case of the particular solution, as is given n into k1 u of n plus k2 into u of n. Substituting this in the expression of the difference equation, we get it as, for y of n we write it as k1 of n plus k2. For y of n minus 1, wherever there is n, we replace it by n minus 1, and for n minus 2, wherever there is n, we replace it by n minus 2. So it is k1n plus k2 minus 1 by 4 k1 n minus 1 plus k2 minus 1 by 8 k1 into n minus 2 plus k2, which would be equal to n, which is going to be equal to the input at x of n. U of n is 1 and n minus 1, because it is x of n minus 1 and u of n is going to be 1. So it's going to be n plus n minus 1. Equating the coefficients of n and n minus 1, we would be getting the solution as 16 by 5 and minus 104 by 5. Thus, our expression would be yp of n is going to be equal to n into k1, which is 16 by 5, into u of n minus k2, which is minus 104 by 5. That's why the minus sign here. 104 by 5 u of n. Let us consider a simple quiz for the linear constant differential equation and difference equation. Determine the order of the system given by y of n minus 1 by 4, y of n minus 2, minus 1 by 8, y of n minus 2 is equal to x of n plus x of n minus 1. The solutions are 2, 1, 3 and 0. We know that we have got 2 storage elements, hence the order of the system is 2. The second quiz has a circuit has 3 energy elements, 2 capacitors and 1 inductor. The order of the system is 2, 3, 1 and 0. Any guesses? Yes, it is 3. Thus, the solution is 1A and 2B. The references are, as usual, Oppenheim and Simon Haken.